There we go. All right, can everybody hear me okay?
Yep, it looks good.
Okay, cool. So maybe give like another like 30 seconds to let people in. Let me check that I've fully let in everybody. Huh. Whoops, I forgot to get people to, join so they could like, I don't know, participate in class. Hello. We will get started in somewhat shortly. Yeah, just let people filter in and we are probably good. So, all right, this is a very special meeting because unlike previous meetings where we go over concepts that you might necessarily know, if you've attended every meeting, each of these concepts should be familiar to you. So I'd like to take a moment and thank each and every person who submitted problems for us to consider. So thank you to everybody who did that. Wait, what is that? Nobody did? Oh well, maybe next time you guys will be more willing to discuss the trickier problems. So yeah, as most of you probably know, I am Justin, former MathCounts USMO competitor. I'll be going over today. The TA is Andrew Kai. He will answer all your questions. So if you have like questions like while I'm talking, direct them to him. It says review 1 twice on the classes page because there's a separate review for introductory level problems and intermediate level problems for Wednesday. So if you want to see both of them, then come back on Wednesday. So let's get started. So we're going to start by reviewing Unit 1 or Week 1. And these are just basic algebraic tricks. All right, these are things that like make solving polynomials and other expressions just a little bit nicer. So a simple example is, let's say we wanted to solve this equation, x to the fourth minus 13x squared plus 36. This is a Corsic, and it looks really scary, but there is something that we can do. Anybody have any ideas how to start? Oh, yeah, if I ask you a question, then feel free to message me with the answer. I see square root every term. It's not the most rigorous. Complete the square. Maybe in this case. I'm seeing a lot of factoring. So the idea is we want to substitute and make this actually a quadratic. So we can make it look like a quadratic by doing this. And once that happens, what do we have here? A squared minus 13a plus 36 equals 0. And hopefully, if you remember factoring, we get a minus 4 times a minus 9. So then we have these. And if each of these are 0, we have two separate equations. X squared equals 4, x squared equals 9. So then, as many of you all have already said, x can be plus or minus 2 or plus or minus 3. All right, the main idea is taking this like big quartic and reducing it to something that we know. Here's another trick that comes up in a lot of things. All right, Andrew likes to refer to this as the midpoint trick, where let's say we want to like do something with this expression. But this expression is kind of like annoying to work with. It's not really symmetric. How can we make this symmetric? I see set y is equal to x minus 1. Expanding will actually not make it symmetric. This actually will. And this is really nice because what you can do is, look what you have. Y plus 1. Oh, these should both be fours. I'm sorry. Yeah. And then raise this to the fourth, and then we have y minus 1 raised to the fourth now. Oh, and look, we have this like +1 -1 business going on. Maybe we can take advantage of that. So we use the binomial theorem, but we can expand this to get y to the fourth plus 4y cubed plus 6y squared plus 4y plus 1. But this one is interesting. Y to the fourth minus 4y cubed plus 6y squared minus 4y plus 1. So we see that like we've almost like gotten rid of half of the terms. Y squared plus y to the fourth plus 6y squared. Oh, that's nice. You can solve this by using a trick that's very similar to what we just went over. So it might not have been nearly as obvious in this case how to find the solutions, but with the advantage of symmetry, we were able to reduce it. Yeah, it's cutting into the bottom for me too. I'm sorry about that. So yeah, lots of things. All right, what are other cool things? Oh yeah, other nice tricks. Because the product of these two is 1, we can expand this in really cool ways. We get that it's equal to x plus 1 over x squared plus 1 over x squared plus 2. And just doing manipulations with these expressions, just like squaring these, sometimes comes up. All right, what do we have next? We have some just like things for like simplifying radicals. The example I always think of is 17 plus 12 root 2. How can we simplify this? We actually, factoring this is like difficult. How would we factor this? Okay, let's square this. All right, now we have 17 plus 12 root 2. What does that do for us? Because now we had to take the square root of it again. So I heard somebody say denesting the radical, and yes, that is the process. How do we start this process? You try to make the inside a square. So what do we do, like guess and check? I see. So let's say this is equal to square root x plus square root y, just as a guess. This makes sense. So 17 plus 12 root 2 is x plus y plus root xy, 2 times the root xy. So x plus y is 17. And what is xy equal to? All right, well, it's actually equal to 72. Now, can anybody guess what x and y are just by looking at this? I see a lot of 8s and 9s. I see 1, 9, and 8s. I like the way that you think. And yeah, that's exactly it. You can see this by guess and check, but this is actually, you could actually turn this into a quadratic. Here's how you would do it. You could say like y is equal to 72 over x. So then x plus 72 over x is 17. X squared minus 17, x plus 72 is 0. Like that. So we know that's, so because we can solve for x and y, this is root 9 plus root 8. We can simplify this. 3 plus 2 root 2. Isn't it easier to square x plus y than minus 2xy? That doesn't really do anything for our immediate goal because that just gives us x squared plus y squared. And why do we need x squared plus y squared? We want x and y individually, which is what this method allows us to do. But that's a great question. It's something that comes up a lot. So it's easy to just like get into that habit, but sometimes simple stuff is better. I could also do y equals 17 minus x. Great comments. Yeah, there's another substitution that we could do. Y equals 17 minus x. And then we plug that into here. We get 17x minus x squared equals 72. And that's cool. All right, so that's enough review for now. Let's get to a problem. This is hopefully being recorded. So let me, oh, I hate it when it says this. Untitled presentation. In case you forgot what class we are taking right now. Let's stare at this problem for a minute. Let's see if I can annotate. Oops. Huh.
All right, guys, I think Justin froze. Give him a second. Sometimes technical difficulties arise, so yeah. Um, so yeah, don't worry too much. He'll come back pretty soon. So, anyways, yeah, I guess I'll be here to like fill the time up for like the next 3 to 5 minutes. Anyways, yeah, Justin's frozen. We'll have to wait a little bit until he comes back. Anyways, before then, I guess I'll just talk about like the problem that Justin's going over. So this is about, okay, so Justin's going over the last problem of our first handout. So if you did, okay, I think he's back. All right,
Hello.
all right, all right.
Sorry. Hopefully this will not happen. I think, yeah, Zoom has been crashing unexpectedly. Those of you who went to the Saturday meeting or the last meeting I was a part of, yeah, I think it was Saturday. Yeah, you guys know this all too well. So let me get everything set up so that I can. Change devices is not really an option for me. So what screen am I sharing? Yeah, that's a refresher on what the problem is. Huh. I do not have a potato computer, actually. I don't know what's going on with it, but hopefully everybody's read this, so let me transition to the whiteboard. All right. So now what is the problem? I see a lot of people have the right idea. Yeah. Please try not to like send me the same thing twice because I probably saw it and just didn't have a chance to respond to it. All right, so what people are saying is, oh, let's take a look at similar parts. All right, and those similar parts are going to be like this thing right here and that thing right there. All right, and why is that useful for us? Oh, because we can substitute for that. So let's say that like, let's just bake this in, sort of. X squared plus 18x plus 30 is equal to a. So we substitute that in here. A is equal to 2 root a plus 15. We square that. A squared is equal to 4a plus 60. Can anybody factor this quadratic for me? All right. A minus 10 times a plus 6. So we know by plugging this in, x squared plus 18x is going to be equal to plus 20. Whoops. Is equal to 0. Or x squared plus 18x plus 36 is equal to 0. So okay, so assuming that these two equations are true, can anybody tell me what the answer is? It's not 54. We use Vietas. How do we use Vietas? C over A is the product of the roots. So are you saying the product of the roots in this equation is 20? The product of the roots in this equation is 36? Oh, yeah. Product of real roots. Yes, I am recording. Fortunately. So is anybody like uncomfortable with what I'm doing right now? Like, are there any problems with what I'm doing? I'm seeing a lot of no's. And all of those no's are unfortunately correct because I should not even be looking at this equation. Now you might be asking, how did I get this equation? Well, that was what happens when a is equal to -6. Let's plug in a is equal to -6 into this equation. We get that -6 is equal to 2 times the square root of 9, or -6 is equal to 6. So I was being a bit more evil in this case because I kind of like baited you into doing this. But yes, this is an extraneous solution. All of you who said that there weren't any problems with this, all right, you need to really remember these. So we can't even look at this. So does a equals 10 work? All right, let's check. 10 is equal to 2 times the square root of 25. That looks good. So then we just need the product of the roots of this equation. So that's 20. Does everybody see how I got this? Or does anybody have any questions? Cool. All right. So let's go on to the next section. All right. Equations. One thing. X squared plus 18x plus 20. Because you know how we said that a was equal to x squared plus 18x plus 30? And if a is equal to 10, then this is our equation. So we just move that 10 to the other side. So we have a lot of like different like types of equations. So for example, the most important one is distance equals rate times time. All right, this is the single thing that you need to use to solve any distance, rate, or time problem whatsoever. I cannot think of a question that like doesn't like a question that's purely just rate based that doesn't only need this and like some equations. All right, and there are also a couple of other ones. We have things like Simon's favorite factoring trick, where we factor xy plus 2x plus 3y. is equal to, like, say 7. Can anybody tell me what we do here? How we might factor this? Simon's favorite factoring trick. Factor x, that's not the strategy that we use in this case. Oh, yeah, add 6. And why do we add 6? Because it turns out when we do that, this right-hand side can magically be factored as this. And writing a number as a product of factors, that should be a y. My apologies. I'm going to ask the people who are spamming me in chats to not, because it's very distracting and I need to be focused on teaching right now, not answering your questions.
Please ask your questions to me.
Well, I mean, of course I'm answering your questions, just not the ones that don't relate to what I'm talking about. And then we can solve this a lot easily, air quotes. So let me hope that my computer doesn't fail me. And let's look at the next question. Or am I sharing the right thing? Oh, I got my entire desktop. My mistake. Okay. Sorry, I just wants to and I also will not answer you if you spam. That's another thing. So think about this. Think about how you might do this. This is an example of one of those like Diophantine equations. All right, so has everybody taken a look at it? All right, we'll get started. I might be going at a slightly faster pace from here on out because I like to get through all the problems. So what are we gonna do? Let's take a look at right triangles. All right, right triangles, what do they look like? A, B, C. What do we know about A, B, and C? All right, great. I see lots of things, and I'm glad that they're like balanced, so they all pertain to the problem. So we know that a squared plus b squared equals c squared. Of course, that's a Pythagorean theorem. We know the area is ab over 2, and we know the perimeter is a plus b plus c. So we know that ab over 2 is 3 times a plus b plus c. Right. Triangle inequality, unfortunately, is not going to help us in this case because we want exact numbers for now. So maybe we should try and isolate c, solve for c. And to do that, we're going to actually want to solve for c squared. So we isolate c. Yeah. So what we can do is we can say ab minus 6a minus 6b over 6 is going to be equal to c. All right, does everybody see where I got this equation from? What I did is I subtracted 3a and 3b and moved them all under here. Then I divided by 3 again. So now, if we want to square this now. So now we've just gotten rid of a variable. That's great. So here's what we can do. What we can do is we can like square this. Let's try and bash this, see what happens. Oh, and just because I don't like having fractions, I'm just going to move this over to that side. Multiply by 36? Yes, exactly. So what happens when we square this? Let me erase the top because now we've abandoned all senses of geometric intuition. We are going full bash with this, as all problems should be done. Don't take that advice. That's horrible advice. But so now let's expand this. So we know that we can expand this by squaring each individual term. I see that might actually work out nicely for us. 36a squared plus 36b squared plus a squared b squared. And then we have to combine each of these products twice. It's going to be plus 2 times 36ab minus 12a squared b minus 12ab squared. I just expanded this. You would get the same thing if you did FOIL. What is that equal to? Oh, look, 36a squared plus 36b squared. And isn't that just nice? So now we can get rid of this. We can get rid of this. And we can see that even that all of these have a common factor. So what we can do is we can divide by a squared b squared to get ab minus, I think, oh, these should be 6s, by the way. I'm sorry if anybody caught that. I got a question. Could we have used Simon's favorite factoring trick to distribute that? And Simon's favorite factoring trick is how to go in reverse. All right. If we want to expand, we can just fall back and go to FOIL. However, I am very glad that you mentioned Simon's favorite factoring trick. And sorry for taking so long. Because now we want to factor this expression, like here. This is just what I get when I simplify here. And to that, we do use Simon's favorite factoring trick. What do? We want to make this equal to 144, because 144 is 12 times 12. A minus 12 times B minus 12 ends up being equal to 72. All right, so now we know we want to find the number of pairs of A and B so that this works. So let me ask you all a question. How many factors of 72 are there? I'm getting a lot of 12. Somebody said 12 positive. That's important. Yeah, we don't want negative sidelines for triangles. But, that is a good point, though. Actually, how does that work? Because, yeah, so what would negative, okay, so there are 12 positive vectors. So that means we have 6 pairs. But what would 2 negative factors look like? All right, because A and B are both positive, these negative factors would have to be close. They would have to be sort of close together. So -8 and -9 should work. And that means that A is equal to 4 and B is equal to 3. But if you plug that in, that doesn't work. So that's interesting. So it turns out that there are only 6 solutions. Why am I picking the 6 instead of 12? I see, because you need to pair them up. And because order doesn't matter. This triangle and that triangle are still technically the same. Four and 3 don't work because they just don't if you plug them in. I'm not sure. Yeah, because then I think this is negative instead of positive. So that's what makes it weird. Somebody asked me a great question. How do I know I wanted the add the 144? I wanted like this plus 72 to turn into a plus 144. That's because that negative 12 times negative 12. So you see how these negative 12s like also appear right here? So if we expanded this, that last constant term would be the product of these two. So I know the product of these two is 144. So that's why I want to put it there. And this is vital to using Simon's favorite factoring trick efficiently. All right. Great. Glad that was able to help. I just erased everything, so that would be why. All right, we're already halfway done with class, and I need to like be somewhere like right at 4. So I am going to just go on straight to the next question. This is a mouthful, so spend a minute, look at it. For the people who said that they don't remember Vietas, this will be a great place to review that. So the reason that we do want to use Vietas in this is because like it's basically just the best thing that we can do short of factoring the entire expression, which is oftentimes impossible. It probably is impossible right here. So R plus S are roots of R comma S of x cubed plus ax plus b. R plus 4, S minus 3, roots of almost the same thing. I'm writing up the problem right now. Compute. I can't even spell. All right, and this is just going to be the sum of like all possible values of this. This just computes, so I won't really worry about the answer format. Like once we solve it, that's all that really matters. So we have these two roots right here. But we really need a third root to get everything else here. So we know R, S, and T. Let's just say T is the root. So is there any nice property about R, S, and T that you can tell me by Vietas? Oh, excellent. So many of you are messing up. I can correct so many mistakes. There is not a T. I came up with T because I wanted a third root. I see a lot of negative A's, and that would be correct if this was a quadratic, but it's not. It's a cubic. So how do we handle cubics? Well, it turns out we need a term that doesn't exist. All right, in order to find the sum of this roots, we take the negative of this coefficient. So it turns out that S plus T is equal to 0 because that's this coefficient here. All right, and let's just refresh ourselves what Vietas formulas are. This A is going to be the answer to this. And it turns out we keep this positive. So we took the negative of this, but it didn't matter. And we took the positive of this. So the next one, we actually take the negative of. RST is equal to negative B. Just like that. Right? I see T is equal to negative R minus S. Yes, that is true, but I'm actually going to keep it like that just to enforce some sort of symmetry. All right, now let's try and look at this next quadratic. We've basically just juiced this cubic of all the information that we have. So let's try and see if we can apply that here. So my first question to you, can we find the third root of this in terms of variables that we already know? And if so, how would we do it? What do we substitute? What is this? We're using Vietas again? That's an excellent idea. All right, because there's no x squared term, the coefficient of x squared is 0. We know that r plus 4 plus s minus 3 plus something else is equal to 0. And it turns out you can actually pick t minus 1. Because we already know that r plus s plus t is 0. So nice, we've gotten something good. And look, we have equations that we can take advantage of. So this is going to be a bit brutal from here on out. So I'm going to skip a lot of the steps. I'm trusting most of you that you can handle the computations. The full write-ups for like all the gory details will be on the docs. So looking at this coefficient and that coefficient, we know t minus 1 times r plus 4 plus s minus 3 times t minus 1 plus r plus 4 times s minus 3. This is the second symmetric sum, and it equals a, just like before. So we can solve this, and we can actually equate this here. And after enough steps, we actually get s is equal to 5r plus 13 over 2. And then we can plug this in back to here. And now we get an even simpler expression for t, or barely simpler. Afterwards, we plug this into this product. What is this product is equal to? We know that b is equal to negative RST. And we know it's also equal to negative t minus 1, r plus 4, s minus 3, minus 240. Where did I get this? I took the product of the roots by Vietas that's equal to this entire thing after I negated it, of course. Then I subtract 240 to also get b. And then you can substitute and solve, and it's horrible. And we don't have time for trifling algebra right now. So we get two types of solutions. All right, this is one. This is another. Negative 5, negative 6, 11, and 1, 9, negative 10. So overall, we just take the product of these because remember b is equal to RST. Is there a better way? Probably not. This is an Amy problem. They expect you to have lots of time to bash. It's just that we don't because I'm trying to get through this in 6 minutes. And I don't have like a huge amount of space compared to my handwriting size. We get the product of these, take the absolute value, we get 330. Product of these, take the absolute value. And our answer is an excellent number. That. Is anybody lost? If so, I'm like afraid I'm not going to be able to help you like that much because I want to get through the rest of the problems. So let's push on. So here's the next problem. This is for a counting thing. All right, and it turns out that this is actually going to be really useful for our recursion. All right, so I'm gonna set up the recursion. It's not the most motivated thing, but here, I'm scared that this will break it again, but let's try and annotate it. Oh, did I? Whoops. Spacey is just like the definition. Like a set of integers that includes 1 and 2 is bad because 1, 2, 3 are consecutive integers. So yeah, let me just do a whiteboard. Ooh, I forgot that we didn't clear that. So what are we gonna do? Let's and Pineapple made a very good points. The null sets or the empty set is spacey. So we should start k is equal to 0. So s of 0 is going to be 1 because there's only one empty sets. S of 1 is going to be 1 because there's only one set that has biggest term 1. So s of 2 is also going to be 1, and s of 3 is also going to be 1. All right, these are the sets that work. So now let's take a look at s of k in general. All right, so we have 1, 2, all the way up to k. So we know that k is going to be included. What about k minus 1? Can we say that k minus 1 is included? Yep, I lost everybody. Great. So by definition, we're including k in this sense because we're counting it as part of x of k. But remember the spacey condition. K minus 1 and k minus 2 can't be included because this is a set of consecutive 3 numbers. So I should not have put a check there. I should put an x there. K minus 3, however, we can have that. And then the largest element of whatever's left is just s of k minus 3. K minus 4. Let's say k minus 4 is the next largest element. We have another x and then a check. That's just s of k minus 4. And all the way down to s of 0. So it turns out we have this, and this looks like a really scary recursion, but we can actually simplify it. Because a trick with recursions is finding some similar parts. So if we just shift all these indices by 1, we get that these line up perfectly. S of k is equal to s of k minus 1 plus s of k minus 3. I got a great question. If k minus 3 works, shouldn't k minus 4 not work? Okay, so the thing is, if k minus 3 works, that doesn't mean that we have to include it. So let me get a better diagram set it. Okay. We know that this is good and this is bad. This is bad. All right, let's say we did make this check. Then everything like here is just the k minus 3 case. That's where we got this term. Otherwise, it could have been an x. We don't know. And then this is a check, and that's where this comes in. So we're just continuing down this ladder like that. So it turns out that, let's just take this recursion on faith. We go 1, 1, 1, 1, then 2, 3, 4, 6, 9, 13, 19, 28, 41. And when we add them all up, we get 129. Neato. So, sorry, I cannot answer questions right now because we need to get moving. That's weird. Okay. We're going to look at this question, stare at it for a minute. I can go back. Sorry, I can't I want to get through the rest of these and I'm like kind of pressed for time. So I also deleted the whiteboard's contents. So all of these solutions will be on the handout that is very, very close to being done. It will be released very shortly and then you can go take a look at their solution. Yeah, so this is going to be a GCD question. And for this GCD question, we're going to be using our old friend, the Euclidean algorithm. Does anybody need a refresher on what the Euclidean algorithm is? Yes, please. Oh, okay. So let's pick two numbers that look 52 and 91. I'm just going to write a G instead of GCD because I'm being lazy right now. So it turns out that we can actually do this. Like the GCD shouldn't change even if we just subtract like one of these numbers like that. So that's, you don't remember the question. I will rewrite it, sort of. This is just Euclidean algorithm, 30. So we can do this again, subtracting here, 13 and 39, and then this is a lot easier to figure out than that. But is anybody still confused about how it works? I'm just subtracting numbers from each other at each step. Where did the 13 come? I subtracted 39 from 52. Right. The 39 is still there because you're not subtracting anything from it right there. Is there a proof for that? Yes, it's long. I don't have time to get into that. Okay, here is the problem. A of n is equal to 101 plus n squared. D of n is GCD of an plus 1. You could continue it, but at that point, you can just look at it. You can continue it all the way down to 0. Maximize dn. This is the question. So let's see what Euclidean algorithm gives us. Let's start by writing it out. GCD of 1, this should be 100. 100 plus n squared, and 100 plus n squared plus 2n plus 1. Like that. So what are we going to do here? Well, we can use the Euclidean algorithm. We see these similar parts. Recognizing similar parts is so important. And once we subtract them, it's already nicer. So now this next step's a bit weird. What we're going to have to do is we are going to get rid of this constant term and maybe change this to something we can factor. So we're going to subtract 100. We're going to subtract this 100 times. So now we're at this step, 200n. And this is n times n minus 200, of course. So now n and 2n plus 1 are not going to have any common factors. You can check this by performing the Euclidean algorithm on these two. That's a great exercise. Just to get practice with it. So because of that, we actually don't need to worry about this. And let's continue one more. You're going to get rid of n on one of the sides. Subtract this twice from here. We get a 401. And now this 401 is important because the 401 is not going to change no matter what we do. So what is the maximum possible value of this greatest common divisor? Where n is whatever you want. This number right here. If n is like 601, it has to be this because the GCD, like a divisor of 401 is going to be less than. So does everybody understand that problem? We actually don't need n in this case. All we just need to do is that GCD. So hopefully nobody has any questions over that because I have given you plenty of time to ask them. Yes, the answer is just 401. All right, 2 more questions left. This one's a nasty one. All right, and yeah, let's just get into it. Last 2. All right, first off, there will be a handout for this review class, yes. The last digit will be 0, which is why I specified that there are non-zeros. Yes, the problem writers are 1 step ahead of you. So now what are we going to do here? Well, how many zeros are at the end of 90 factorial? I see 21, I see 9, I see 18. The way that we calculate this is we take 90 divided by 5, and that's 18. And then we take 18 divided by 5, and that's 3. We take 3 divided by 5, and that's 0, so we stop. So 21. So we want to look at 90 factorial over 10 to the 21 mod 25. Or mod 100, I'm sorry. So why does this matter? What we do is, oh yeah, I forgot to put floors here, but all right, what this does is this is 90 factorial, except the last 2 digits are the non-zero ones that we want, as desired. So if we're to evaluate this, we need 2 parts. We need 90 factorial over 10 to the 21 mod 4 and mod 25. What is this mod 4? It is 0. There are a lot of 2s in this expression. So let's find this mod 25 instead. And this is going to be tricky. So what we are going to do is we are going to go we are just going to write this out as 1 times 2 times 3 times 4 times 5 times 6 all the way up to 90. Except we're going to cross out 5s from each of these all the way up to 18. So we have 1 times 2 times 3 times 4. And then we're going to have 6 times 7 times 8 times 9. And all the way up to 86 times 87 times 88 times 89. That's going to be cut off. So do you see what I just did? I just divided out all the 5s, but 5 to the 21 here. And I'm still going to have to divide by 5 to the 21. I'm still going to have to divide by this, but hopefully that will not be bad. So now it turns out, and I'm not going to prove this right now, you can try it if you want, that each of these products is going to be -1. Why did we get rid of the 5? We got rid of these 5s. Like, you can think of it like taking this 5 to the 21 and baking it into here. So this is -1, -1, and then -1 at the end. And then this product right here, it's going to be 1, 2, 3, 4. We're going to not skip the 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16, 17, 18. And yeah, this is a lot of work. Why are we taking it mod 25? Because mod 25 and mod 4 combined is mod 100 by Chinese remainder theorem. And wait, Andrew, I am correct in like all these like products of 4 things is -1, right?
Mm-hmm.
Okay, good. It's been a while since I've done this problem. So all of these products are going to cancel out because they come in pairs of 2. These 2 are going to cancel out. This becomes negative. 16 times 17 times 18. What is that going to be? Well, let's figure it out. 16 times 17 is 272. So that's going to be -3. Mod 25 times 18, -54. So that's -4. So this entire thing is just 4. But we still have to divide by 2 to the 21. So we get that this entire product is 1 over 2 to the 19. Wait, Andrew, do you remember the answer?
Not exactly.
Okay, I hope this works out. I will check with Wolfram Alpha. And it turns out that there is a theorem that says that like this is like 2 to the 20th is congruent to 1.
Actually, yeah, I have it.
What is it?
12.
Okay. Thanks. Oh, that is not what we are going to get. So I screwed up somewhere. Yes. So am I. I'm sorry about this. I try to rush this and okay, so there's going to be a question that we will not get to because I'm going to have to leave. Wait, Andrew, are you fine if you take over the last problem?
Give me a second. Sure. I don't have anything to write. Yeah, I'm all right. I'm good with
Okay.
that.
You can just like scroll through the handout.
Yeah, just finish up this problem.
Yeah, okay. I need to like do it correctly though.
Mm-hmm.
So where did we go wrong? Let's clean this up. We are going to get through this. You think I messed up on the 4? Probably. Okay. So, and I'm going to use this opportunity to explain what I'm doing. So we were trying to evaluate this. All right, hopefully everybody's okay with this part. And the thing is, dividing by 5 mod 125 is incredibly dangerous. So I want to sort this product out internally. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then all the way up to 80, 86, 87, 88, 89, 90. So what I can do is I can get rid of the 5s from each of these. This becomes 1, this becomes 2, all the way up to 18 right here. Oh, I think I see what I did. Excellent. 4 times 2 times 3. Yeah. Oh, okay, good. This works out. So what you can prove by yourself is it turns out when you take these groups, they will multiply to -1 mod 25. I don't know how you're supposed to motivate that. It seems like magic to me. But you see that, okay, this means that we can actually like ignore these groups right now. Because this multiplies out to -1, this multiplies out to -1, so that cancels. And there's going to be cancellations on each row. So all we're left with is this like 1, this 2, and so on up to the 18. We have to be a bit more careful because we can't have any 5s. So you have 1, 2, 3, 4. It would be a 5, but instead we have a 1. 6, 7, 8, 9. I'll explain what I'm doing. All right, so they should be 5, 10, and 15, but they're also not needed because we divided by 5, so we have to be careful about these. -1, -1, -1. So this is -1, and this is -4. I got that right. And this is 6. So the overall product of all of these terms, when we multiply them, is going to be 24. Great question, Cordy. Mod 4 is not needed because this is definitely divisible by 4. So we know that this product is just 24. So we need to evaluate 24 over 2 to the 21, which is 12 over 2 to the 20. And 2 to the 20 is actually equal to 1. That's a number theory theorem that I don't want to get into right now. So this is 12 mod 25. And this is also 4 mod 4. So the overall answer at long last is 12 mod 100. And that's where we finish. Sorry it took so long to get here. So yeah. All right, Andrew will walk you through the last question. I have to leave right now. Thanks
All right,
y'all
see you,
for
Justin.
coming. Is the recording going to continue when I leave?
I think so. I'm not entirely sure, but it's.
Did
I
it?
think it
Did
will.
he continue when I
Yeah, it
zipped?
continue.
Okay. See y'all.